everybody. This is Professor H. Rahman from Agricultural and Food Engineering Department, IIT Kharagpur. I welcome you all to this NPTEL course on traction engineering. This is lecture 24, where I will try to give description about how to evaluate the performance of a walking tractor when it is fitted with truck. Wheels and trucks, these are the two common traction devices which are usually fitted with tractor. When I said walking tractor means this study is confined to the power tiller. Since power tiller is operated by a human being who has to either walk behind or who has to sit on a frame to control or to guide the operation of the power tiller. So that's why we call it walking tractor. Since a person has to walk behind the power tiller, usually in a power tiller, a person has to, or the operator has to walk behind. So that's why we call it as a walking tractor. So the concepts which I'll take is the motion resistance, pull, tractive efficiency, slip, net traction ratio. These are the parameters which will be considered for evaluating the performance of a walking tractor when fitted with rubber trucks. So this is the power tiller which has been converted to be fitted with trucks, okay, and the trucks details are given in the right figure, where the log height, log angle, etc. are given, and the pitch of the log, all those things are given, and the tread pattern and the log patterns which are provided in the truck, they are nearly same. Okay. So now the walking tractor will has been replaced with a truck on both the sides, and for mounting the truck we require some modifications in the power tiller. That means we have to provide an idler in the front, and this is the driver roller that is fitted to the axle of the power tiller. That means this is powered, the front one which is idler is not powered, and to keep tension to the truck we provide some intermediate rollers here and here, so that during operation the truck is perfectly horizontal on the surface on which it is going to work. So the details of walking tractor: what is its engine, what is its mass. So engine is VST Shakti, this is the model 130 DI, and this is a diesel engine, 4-stroke diesel engine, and is a horizontal one, and it develops 9.7 kilowatt at 2400 RPM. Its total mass after modification, that means after attaching the truck, comes down to 530 kg. Initially it was 430 kg with pneumatic wheel. When you replace the pneumatic wheel, because of these arrangements, its weight has been increased to 530 kg. Then these are the dimensions of the truck. Width of truck is 0.15 meter, contact length is 0.78 meter, and then diameter of the front idler, diameter of the rear drive wheel, and diameter of the road wheels, all are mentioned like 0.34 meter, 0.55 meter, and 0.11 meter. So to measure different tractive parameters, we need to have some instrumentation for measuring what is the pull which the power tiller or the walking tractor is going to develop, and how much pull it is required to tow this power tiller. For that also we need a kind of load cell. So that's why I have indicated here a load cell which is attached to a frame which is mounted to the power tiller chassis, and this is kept horizontal during operation, so that whatever pull you are getting, that is almost nearly the horizontal component, that is equal to your draft. Then the important component, other important component is the actual wheel speed. For measuring actual wheel speed, you need to know what is theoretical speed, okay, and then you need to know what is actual speed. So for this, what we have done is, for measuring theoretical speed, we have put one spikes here you can see I have enlarged that one. Spikes are present on are fixed to a sprocket which is attached to this ream, and then we have a proximity sensor which will try to sense these spikes, so that it can give a signal to the in the output. Basically, a proximity switch is nothing but it senses the presence of any metallic objects like these spikes. So, once it senses, then it gives a signal. So, that signal or the spike which you are getting in the output will be counted, and the time duration, if you know, then you can find out what is the speed of operation. Similar exercise or similar arrangement has to be made for measuring the actual velocity. So, but in a power tiller, since there are only one drive axle and there is no axle in the front one is the idler which is provided. So, what we have done is we have put a separate wheel which is a towed wheel, and this is mounted to the tractor chassis, the working tractor chassis. So, that speed again has to be measured using a proximity. So, that will give you what is the actual velocity. So, actual velocity, theoretical velocity, then that will give you what will the corresponding slip. So, we need to know slip, we need to know pull, then only calculate the drawbar power, and we utilize this load cell for measuring the rolling resistance. That means we tried, I'll show you the setup, how did we measure the rolling resistance. So, we have measured pull by using a load cell, and you have to measure rolling resistance or the motion resistance by using the same load cell, but the arrangement is little different. If you look at the top figure, the power tiller is used to pull a tractor. That means this is going to give you the drawbar pull performance for different conditions. Now, the lower one is a setup where the power tiller is kept behind, and in the front there is a tractor. So, this kind of arrangement is meant for measuring motion resistance. That means how much force is required to tow this working tractor, that has to be measured. So, for which we put a tractor in the front, and closer to the tractor we put a load cell. So, and with the help of wire we try to connect the power tiller with the load cell and the tractor with the load cell. So, the power tiller is kept idle in neutral, and then the tractor is going to pull it at a certain speed. Speed could be 1 km/h or speed could be 2 km/h. Then we try to find out what is the output from the load cell, and that is recorded in a data acquisition system, and that is recorded in a computer through a data acquisition system. So, by this we can find out how much is the force required to move this power tiller. So, that becomes your motion resistance. Now, if you look at the top figure, we are interested in finding out pull developed by the working tractor for different conditions. Different conditions means maybe the slip, different slip values. So, how do you control slip here? Here basically we are not controlling slip. Here the power tiller is in the front, tractor is in the back side, and the load cell is in between. That means it is closer to the power tiller, so that the line of pull is almost horizontal, and the load cell, one end of load cell is connected to the tractor and the other end is connected to the power tiller. So, when we try to find out what is the pull developed, so you have to run the tractor at a speed which is lesser than the speed at which we want to operate the power tiller, so that the tractor can exert some pull. Okay. So, by reducing the tractor speed, you can vary the pull, and that pull has to be measured along with the wheel slip. So, that will give you how much drawbar power which is developed by the power tiller. So, this data related to pull and the slip. Slip means the actual velocity and the theoretical velocity. All these informations, they are collected through a data acquisition system and stored in a computer. These are the basic instrumentation which is required to carry out this kind of study. Next, the data which we obtained that we try to plot. The first is motion resistance. So, motion resistance versus travelling distance. This has been plotted for 3 different soil conditions. That means we varied the soil conditions starting from 250 kilopascal to 1000 kilopascal, the average value I am talking about. So, that means when the soil cone index is 250 kilopascal plus or minus 50, that we take as soft soil. When the soil cone index is 500 plus or minus 50 kilopascal, then we take as medium soil, and when the soil condition is 1000 plus or minus 50 kilopascal, we take as hard soil. And for these 3 different soil conditions, what we have measured is the motion resistance, and the values are 1012 in 250 kilopascal, that means soft soil, 775 Newton in medium soil, and 620 Newton in hard soil. Soft soil gives maximum motion resistance as compared to hard soil. Same is the case for motion resistance ratio. It is maximum in case of soft soil and minimum in case of hard soil. Why it is so? Is basically due to sinkage of track in the soil. Since the soil is soft, maybe it does not sustain the weight of the track. So, there might be some kind of compaction and sinkage. So, that creates or that require more force to tow the working tractor. So, when the soil is hard, that sinkage is less. So, you require less power to tow it, or you require less force to tow it. So, that is why motion resistance is less in case of hard soil. This is one of the parameters which you are interested, and this has to be, and this was found that rolling resistance variation or the motion resistance variation with slip is not that much, it is very minimal. So, that is why in all calculations we have taken this as the motion resistance for different pulling conditions. Now, coming to drawbar pull. The pull which is sensed by the load cell, that we try to plot versus wheel slip. Again, for 3 different soil conditions, we got 3 curves. The green one is for hard soil, and red one is for medium soil, that is 500 plus or minus 50 kilopascal, and the blue one is for soft soil. So, nature of the curve is similar in all these 3 soil conditions. That means it initially increases at a faster rate, then slowly it reaches to a peak. After that, it remains almost constant. So, the pool which is developed in hard soil and the pool which is developed in soft soil, they are not same. So, there is a variation in the sense there is a difference. So, at different slip values starting from 15, 20 and 25%, I have given the pool values, the drawbar pool which is developed. So, if you look at this, so the maximum drawbar pool is developed in 1000 plus or minus 50 kilopascal. That means, in hard soil, pool developed is much higher than the pool which is developed in soft soil, whether it is 50%, 15% slip, whether it is 20% slip, or whether it is 25% slip. So, this is because of the rolling resistance, because rolling resistance is more in case of soft soil. Even if the tractive effort developed by the power tiller is same, because of the higher rolling resistance, much power is lost due to that, then the net pull is reduced. That could be a reason. Okay. Now, if you look at the medium soil, it is lying in between these 2 soil conditions. One is the hard soil, the other one is the soft soil. Now, quantified how much is the reduction. So, we can see here pull developed by working tractor was higher in hard soil condition and a decrease in the soil as the soil becomes soft. Okay. So, peak tractive efficiency, which is derived from this pool and coefficient of rolling resistance. So, together we have to take to find out peak tractive efficiency. So, that values it has been indicated like 51.15%, and what is the corresponding sleep. Similarly, in medium soil it is 63.3%, and what is the corresponding sleep, and in hard soil it is 70.7% at around 10% sleep. So, for 3 different soil conditions it has been given, and let us now see the nature of the curve. This is tractive efficiency, which is nothing but pool by tractive effort, which is nothing but P plus R into 1 minus S. Right. So, I have not written W here because W remains same, that is I am cancelling this one. So, only I have taken P plus P by P plus R rolling resistance or motion resistance. So, the nature is tractive efficiency is reaching to a peak value after certain sleep. So, if you draw a line here, this is the sleep, this is the sleep where it is getting, this is the sleep where it is getting maximum. Then after that it is slowly going down, and the rate of decrease is more in case of hard soil. So, the nature of the curve is same. Initially it rises to a peak at a faster rate, then it goes down. So, the initial reduction in tractive efficiency is because of the power which is lost due to overcome the rolling resistance, and after 20% sleep, whatever reduction is there is because of the wheel sleep, the track sleep. So, the power is lost because of the higher sleep. So, that is the reason we are getting a peak at a particular value or in a particular range of sleep value. So, the maximum tractive efficiency which is developed by the truck was 51.15 at a sleep of 16.8%, and that is in case of a soft soil here 16 point somewhere here, and for medium soil it is 0.63 somewhere here. So, at a sleep of 11.85 somewhere here, and for hard soil we are getting a maximum value of 70.7 at a sleep of 9 point. So, sleep at medium, sleep at hard soil, they are very close. So, that means within 10 to 11% or 12% we are getting the peak values, whereas in case of soft soil we are getting a peak value beyond 15%, but nevertheless it is lesser than 20%. Our maximum target is 20%. Let us see now the plot, a different plot where we will see the effect of all the parameters, performance parameters. That means on y axis we have traction ratio, on slip ratio, and on the x axis we have net traction ratio, which is nothing but your coefficient of traction. That means the dotted lines are indicating the tractive efficiency for 3 different cell conditions. The green one is indicating for 1000 kilopascal, the red one is indicating for 500 kilopascal average, and the blue one is indicating for soft soil. And the lower 3 solid lines, the green one is for 1000 kilopascal, this is a sleep value, and the red one is for 500 kilopascal, this is sleep value, and the blue one solid line is indicating the sleep value. So, trucks usually achieve a peak tractive efficiency at higher NTR, that means higher net traction ratio. If you look at the peak value, it is somewhere here in hard soil, and in case of medium soil it is somewhere here, and in case of soft soil it is somewhere here. That means the NTR value maximum we are getting is 0.3 in case of soft soil. In case of medium soil it is 0.36, 37 like that, and in case of hard soil it is beyond 0.4. So, I have summarized the performance parameter like maximum tractive efficiency, slip at maximum tractive efficiency, what is the NTR at maximum tractive efficiency, and the efficient NTR range. This is one parameter which I have found out from this curve. So, if you look at the values, again maximum tractive efficiency values are given. So, it is maximum in case of hard soil and it is minimum in case of soft soil. And the peak which you are getting in soft soil is at a higher slip, that is 16.8%, and the peak 0.707 which you are getting is at a track slip of 9.96% in case of hard soil. And the corresponding NTR, you can see it is more than 0.42 in hard soil, it is 0.366 in medium soil, and 0.29 is roughly equal to 0.3. Now, I have defined a terminology efficient NTR range. That means, if you look at the curve, you can see you are not getting the peak at a particular point. You are getting a peak at a wider range of NTR. This is the range you can say for medium soil, and for hard soil this is the range. So, that range I have taken as the efficient NTR range. That means, the track can able to develop maximum tractive efficiency for a wider range of pool values. So, when I said NTR is nothing but P by W. That means, for a pool value of 0.24%, 24% to 37%, there we are getting the maximum tractive efficiency in case of a soft soil. In case of medium soil, it is varying from 27% to 43%, and in case of hard soil, the range is still larger, in the sense 31% to 47%. So, that means the track will perform better for different pooling conditions, which is not the case in case of a wheel type tractor. So, the three parameters, if you look at coefficient of traction, then tractive efficiency, and the other parameter is slip. And let me discuss a little bit about slip. If you look at slip nature of the curve, you can see traction ratio is varying with slip. So, it is reaching to a peak, then it is going down. It is reaching to a peak, then going down. That means, the slip is increasing in case of soft soil. To get the maximum peak of tractive efficiency, the slip is more in case of soft soil as compared to hard soil. So, that is the reason why the tractive efficiency is less. Okay. So, higher slip means most of the power is lost in overcoming the rolling resistance. So, that is why you are getting a lesser tractive efficiency. If you summarize this one, what we discussed, from the these are all field experimental data. So, that is why from there we concluded like this: rubber track experience a higher motion resistance in soft soil, and the loss due to motion resistance decreased with increase in strength, soil strength. The pool which is developed by walking tractor was higher in hard soil condition, and a decrease as the soil becomes soft. Peak tractive efficiency, which is obtained as 0.51 at 16.8%, 0.633 at 11.85%, and 0.707 at 9.96% wheel track slip for three different cell conditions like 250 kilopascal, 500 kilopascal, and 1000 kilopascal. Then the peak tractive efficiency, it was higher at higher NTR values, and this higher peak tractive efficiency was prevailing for a wider range of NTR. That is the plus point in case of a truck. Then the maximum tractive efficiency which is obtained, which I have already discussed, I think. So, there is maximum is 51% in case of soft soil, and in case of hard soil it is 70%, and the slip is within the limit of 20%, because in case of wheels we usually take wheel slip to be 20%, within 20%. But what we are observing here is, in case of a truck, maximum is obtained less than 20%. So, in this lecture what I have attended is, I tried to discuss about the measurement techniques, how to measure the different performance parameters, tractive performance parameters like rolling resistance, pull and slip, and then try to discuss about the data which is obtained, the data which are obtained related to a walking tractor fitted with trucks. And there we try to discuss what is the nature of the curve and how the tractive efficiency is varying, and how we observe the important thing which was observed is the range of tractive efficiency, maximum tractive efficiency values. So, that is more important. That is all. Thank you. So, this study has been taken, like this field experimental data was related to the experiments which we conducted at IIT Kharagpur, and some of the papers we have published, and based on those data we have discussed this thing. That is all. Thank you.